Technical Director.
All right.
Go for it.
Hi, Steve Williams from Track. I'm here today with John Bushy, Technical Director for American Standard Circuits. We're going to talk about a couple bleeding edge technologies. The first one, John, is plated copper via holes.
Yes, what we're talking about today, Steve, is copper plating filled vias, or micro vias in this particular example. And what we're generally talking about is any type of a blind via structure that has copper plating filling the entire depth of the hole. So this would be an alternative to conventional polymer via filling technologies that have been around for a while, both conductively filled and non-conductively filled. This would be the epitome in electrical and thermal performance, and also more readily allows the formation of stacked microvias to make multi-layered sequential laminated structures.
Is there a reliability boost with this type of structure?
Anytime you go to a solid metal, there's a potential for an increase in reliability. And that was one of the thoughts behind this, because you don't have a vastly dissimilar material filling the hole. You're not going to have a difference in CTE, at least locally. So it does potentially offer some advantages. I believe people have done several different studies on the increased reliability of this type of structure. And we're beginning to integrate it here at ASC in order to develop the technology in stacked microvias. So when we're talking about this, the first thing or the first step is going to be to create the hole. How are we going to form it? And there's two options here. We can use either mechanical drilling, or we can use laser via formation. We tend to use mechanical drilling here just because we've made the commitment to that mechanical technology. Currently, we are mechanically drilling 3.9 mil blind microvias, conically shaped, although we do straight drilling down to that diameter as well. But it asks the question of, what is the shape of the hole? And there is a slight difference. A conical drill is going to yield almost perfectly shaped conical shaped hole, whereas a laser formed via is going to have kind of a bulge in the center of it. Neither one is necessarily better or worse than the other, but a mechanical drill has some advantages in that it leaves you a known quantity at the bottom of the hole. So when you have bare copper, or you hit the copper, you've got exactly bare, pristine copper. Anytime you use laser to form that same via structure, you've got something in the bottom of that hole that is an unknown quantity. It's some residue of whatever materials were ablated above that layer. And so you have to consider that when going into the next treatment operations.
So, John, how does your equipment know that it's hit the copper and that's the depth you want?
You have to know mathematically exactly how thick this dielectric layer is, along with the thickness of this top copper. Nowadays, modern drilling equipment has what's known as contact bit detection, or at least a lot of it does. In this particular instance, it uses capacitance, or once it contacts that top surface of the copper cladding, it can tell that there's a large amount of capacitance in that large copper plane. It senses that as the top layer and begins measuring down from there. So if you know the distance or the thickness of this copper, the thickness of this dielectric, and know what percentage of this inner layer copper that you want to penetrate, you can then calculate that distance and set your depth based on that information. So when we mechanically drill, we're going to drill and penetrate slightly into this sub-layer. And basically what you're left with is a clean copper surface. It's basically been mechanically drilled. It's removed a small amount of the copper. There's very little material removal in this operation. There shouldn't be a lot of heat generation. The requirements in drilling are a little bit different, in that it requires relatively high vacuum for this particular type of drilling, just simply because you're trying to evacuate from a very small tool, very high RPMs, and you don't have a lot of free area to be able to evacuate those chips. So in the formation, not a huge difference between the two technologies. It's just that we happen to prefer the one as a known quantity of an exact hole shape, and we know what the copper is beneath it. Next is treatment. What are we going to do to ensure that there is clean surface on the bottom as well as clean interconnects on the top layer, as well as to make sure that we've got the correct roughness or surface area to be able to subsequently metallize. In that particular instance, we generally prefer to use plasma, which is a variety of different gas cycles in order to achieve both an effective desmear or removal of any excess resin, as well as an O2 burn to remove any potential ash. Now, there are other mechanical operations that we go through to ensure proper wetting for the next step. We want to make sure that those holes are completely clear, so we will generally go through a hole cleaning operation with multiple different steps involved, such as ultrasonics, high pressure spray, etc. Next is metallization. We need to have a copper, electroless copper plating solution that's capable of moving in and out of that small diameter of a blind feature very readily, as well as the ability to be able to plate or deposit the copper into that via what's essentially a very small cavity. That's something that we've invested in recently in changing technology in our copper, electroless copper supplier, specifically with that goal in mind. Next, we're going to move on to what we'll consider the key technology in this particular process, which is the copper plating. And it differs from a traditional electrolytic copper plating bath in that we're not simply trying to throw copper down a deep hole and keep it relatively the same thickness or throwing at the same rate throughout the depth of that hole. In this particular instance, we're concerned about doing it in two different steps. One would be the filling operation, where we use one specific current density with a very specific copper plating solution with specific via filling additives to preferentially plate down in the bottom of the hole as opposed to the surface or the sides of the hole. And step one, at one current density, we will fill the hole approximately 50% of the way from the bottom up, only adding a small amount to the sides and the surface. And in the final step, we'll use a higher current density to do the finished plating. And what that does is it plates in preferentially from the sides, and eventually it just closes the hole up. Now, the finishing of this type of a via, there will always be some slight dimple as it continues to close and close and close, but there's extra additional copper that's plated onto the surface, which is subsequently planarized flat to form the surface for either a surface mount land or for a subsequent stacked microvia. So that's the long and the short. Specialty drilling operations for very small microvia formation, specialty plating solution, and a different methodology used for the plating cycle itself. All told, what you end up with is a via that is solid copper filled, giving you the best of mechanical properties, electrical properties, and thermal properties.
Great. So the first stage is a low current density. The second step is to crank that up and put it in. And then you've got some post-processing you do, right?
There will be a planarization step, basically, to first of all reduce or eliminate any dimple that would have formed during the closure operation, but also to remove additional surface copper, because in most cases we're trying to form very fine line and space structures because of the density of these types of boards.
Did you have to have any new specialized equipment to do this, or plating systems, or?
What we did is we basically designed and built plating cells specifically for this process that required new rectification, which is actually programmable to be able to automatically do the stepped plating function, so that it doesn't require intercession by the operator in order to perform these cycles once they're established by process.
Okay, great, John. I appreciate that. I learned a lot. I'm sure our audience is going to learn a lot from Master, and I appreciate your time today.
All right, Steve.
All right, we look forward to the next one. Thanks, John.